we are recording. So hello, Math9 students. We are going to be working on section 8.3 today, which is actually the last section for Unit 8. So Unit 8 is a little shorter, and I think the reason that it's shorter in the text is because the concepts are I would say more difficult. They require a bit more thinking and critical thinking skills, processing, because you're not just using some sort of formula in order to get from the beginning of a question to the end of a question and find out a numerical answer. You actually have to kind of think outside the box on this one, and you have to prove and justify how you're coming up with certain calculations. So it is a bit more difficult than other units in that respect. Again, some people take to it really quickly, and others really struggle with it. And I will say, of the 3 sections in in Unit 8, 8.3 is definitely the most difficult. We're dealing with circles and angles and some properties that they kind of sound similar, but there are some key important differences. Also, after we're through 8.3, there's an expectation that you can kind of put all of these theories, all of these properties together to solve more in-depth questions. If any of you have looked at quiz 8.3 yet, you probably are a little bit anxious, because the questions in 8.3 do represent a sort of a significant jump up from 8.1 and 8.2. But I assure you, I'll give you some hints for them, and I'll get you sort of thinking in the right direction, and I think you'll be able to fill in the missing pieces yourself. Okay, so without further ado, we will get on with the notes. I'm just gonna fix something on my other screen. So we've already gone through 1, 2, 3, 4, 5. I think we've got 5 properties. No, sorry, 4 properties already that we've discussed. We had the tangent radius property that we used in 8.1, and then we had 3 in 8.2. They're all involving a perpendicular to a chord. So we had the PCP1, PCP2, PCP3. I've marked several quizzes from 8.2, and from what I've marked so far, people are referring to the right or to the correct properties as part of their justification, and that's good. So the ones I've seen so far, people seem to be being able to connect the dots and justify why they're getting certain numbers, certain lengths, certain angles. 8.3, we're going to add 5. 1, 2, 3. 1, 2, 3. No, sorry, we're only going to add 3. So we're going to add 3 to that total of 7. And armed with all 7 of those and understanding of them, you should be able to complete the unit exam for Unit 8 without a whole lot of difficulty. All right, so let's move into it here. A section of the circumference of a circle is an arc. So, pen proper length width here. So an arc. Okay, an arc can be any length. Okay, it could be half the circle, which we would call a semicircle. It can be a portion of the circle. It could be 3/4 of a circle. Those all represent arcs on a circle. So it's basically just a rounded line is all an arc is. In this case, we've got an A and a B point. There's B, there's A. And the bigger arc, there's always 360 degrees in a circle. I think we know that already. The bigger arc in any circle between 2 points is just called the major arc, which means that the smaller portion, okay, is going to be the minor arc. And if it makes it any easier to kind of keep those separate, maybe I'll represent the major arc in red, and I'll represent the minor arc in blue. One's obviously longer than the other, so the longer one's always going to be the major arc, and the shorter one, the minor arc. Oh, I had those backwards, I'm sorry. It started with the shorter arc. Catch me when I do that. Sorry, the shorter arc is the minor arc. I'll just had them backwards. Minor arc. And the longer arc is the major arc. There we go. angle formed by joining the endpoints of an arc to the center of a circle. That is called something, that's called a central angle. And that's probably a new term. You've probably never heard that before. So that's a central angle, meaning it's an angle formed into the center of the circle. And in case you see it in any of my notes or videos, I usually just abbreviate that to CA. So CA just stands for central angle, just so I don't have to write it out every time. So in this case, the central angle, okay, joins the endpoints of an arc. Well, our arc is noted in red there. So the arc is between AB, the minor arc going underneath, and the major arc is the one that goes ACB all the way around the outside. Okay. But we are talking about an angle formed by joining the endpoints of an arc. So in this one, A to the center O to B is the central arc. So the angle that is formed by that is the CA. And then there's another type, because we've got the major arc as well, that the next angle doesn't go to the center of the circle. It starts at the same point, still starts at A, and it still starts at B, or ends up at B. This kind of terrible line there. So it still uses A and B as their starting point, but this time, instead of going to the center of the circle, it goes to a point on the circumference. So a point on the outside of the circle. Anything that goes to a point on the outside of the circle, the circumference of a circle, that's something that's called an inscribed angle. And again, that's likely a term that you've never seen before. So that's called an inscribed angle. And the word inscribed really just means in. So that's where the in part comes from. So it's inside the circle. And predictably enough, I typically refer to them as the IA when I'm providing my justification, just so I don't have to write out inscribed angle every time. All right, so we've got a central angle that goes to the center, and then using the same points on the outside of the circle, the AB, we made it to point C, and then we've got an inscribed angle. And it turns out that there is a relationship between those two angles, and it's always true no matter where this point C is. That point C could be anywhere on the circle, and if you join from A to that point on the outside to B, you're going to find that actually all of those angles are equal, which is kind of a neat little proof about triangles there. And we'll get to that a bit more later because it kind of works in with another property. But for now, I just wanted to kind of let you know that that's an interesting little tidbit of information there, is that all of those angles are equal no matter where you put them on the outside of your circle. I'm just representing this first one kind of straight up and down so that we can just keep it as simple as possible before we move into some of the more complex places that that C point can end up. All right, some more new terminology. That's another reason this unit's so short, is there's a lot of new terminology that you've probably never heard before. The inscribed angles and the central angles in this circle are subtended. So that's a new word right there. I don't think anybody in this class would have heard the word subtended before. All subtended means is that they share the same arc. Okay? So if you want to make yourself a little note there, that just means they share the same arc. And what does share the same arc mean? Okay, they both start and end, depending on which way you're going, at A and B. So any arc that you make in this circle that goes from A to any point on the outside of the circle and then back to B, or from B to any point and back to A, they will all share that red central, or that red minor arc at the bottom. So as long as it starts at A and ends up at B, or starts at B and ends up at A, those angles are going to be termed subtended. They are subtended by the same arc. So that's a new word for you, and you're going to see it in your quizzes in your exam. Make sure you understand what that word actually means. Okay, now on to our first property. Okay, there's a special relationship between the angle that is formed in the center and the angle that is formed at the top in that inscribed angle there. And it turns out, and it's been proven, that the angle that goes through the center, the central angle, is twice as large as the inscribed angle. As long as they both start and end at A and B, whatever that point is on the outside of the circle, if I were to make more, all of those angles are going to be half as big as the one in the middle. So the one in the middle, the central angle, is always the biggest. So kind of keep that in mind as you're going through this unit. So if you know what this central angle is right here, you can figure out what the other angle or what the inscribed angle is, because you just got to divide it by 2. It's half the size. So that's what this is saying here. If we start with P and Q, we notice that it makes a central angle at O. Okay, so that's the CA is right there. And we also note that there is an inscribed angle that also starts at P, goes to R, and then goes to Q, or you could go backwards, it doesn't matter. And that would be the inscribed angle, would be right there. So what the property tells us is the angle POQ is twice as big, because that's the one that goes to the middle, is twice as big as the angle that goes PRQ. Okay? I don't know if it would make much difference, but for example, if I just put for example here, if angle POQ equals, let's just say 70 degrees, then angle PRQ equals half of 70, which is 35 degrees. So that's a very useful property that we can use when we're trying to figure out angles in a circle. You just have to be able to recognize which one is a central angle, which one is an inscribed angle, and there might be more than one inscribed angle, and are they both subtended by the same arc? So do they both start and end with the same points? Because if they do, then you can use that property, and it might save you a lot of thinking later on when you're trying to figure out how the angles are related to one another. So a quick extension of that, and I already sort of mentioned this, is that all inscribed angles that start and end at the same spot, so if they're all subtended by that green arc, they're all equal. So that means that this angle starts at Q, goes to P. Okay, the next angle starts at Q, goes to S, but it still ends up at P. So they're still starting and ending at the same spot. And then the very last one does the same thing. It goes from Q to T, and it ends at P again. And again, it didn't matter if I started at P or if I ended at P. They both start and end at P and Q. And then we put these little notes in our arcs, and those just indicate that any arc that has that little symbol right there, those are equal. Or sorry, any angle that has that little symbol on the end of it, those are equal. So it doesn't matter where on the outside of this circle or on the circumference of this circle you make a point, it's all going to be equal angles. So even if I made my own point, and let's just say I made another one right here, what letter didn't I use here? Let's say I made angle X. If I were to draw an angle that started at R, went to, oh, I'm sorry, not started at R, I'm supposed to start at or Q. Wrong spot. So if I draw another inscribed angle that starts at Q or P, doesn't matter where it is on the outside of the circle, that angle right there is also going to be the exact same as the other colors. Okay? So in this case, P, T, Q, it's Q down here, So PTQ is the exact same as PSQ is the exact same as PRQ, and then I made a new one, PXQ, as an example. So if you find out any one of those angles, you can find out the rest, or you instantly know the rest. Okay? It's not a whole lot of use if you don't know what one of those angles is, but as soon as you figure out what one of those angles is, and the question has to give you enough information for that, as soon as you have one of those angles, you've actually really got all four of those angles, which is very handy. So you've got to kind of use a little bits and pieces of each property in order to get to the end answers on some of the more complex questions. Okay, so let's extend this even a little further. There's a special type of arc called a diameter, and that's a word I know you've heard before. This isn't exactly a perfect circle. It got squished somehow. But the idea is a circle is 360 degrees. Okay? So a full circle and we know this. A full circle is 360 degrees. There's nothing new about that. So a half a circle, and semi means half, right? So a half circle equals 180 degrees, okay? And that is a semicircle. And I think you've heard that word before, but that's what it means, okay? A semicircle is 180 degrees. And in a circle, that's a diameter. And the reason we know that, is that we know that a diameter goes through the center of a circle and then back out to the other edge of the circle. And we also know that the radius in every circle, no matter where you put it, is always the exact same length. So the distance from the middle, from the circumference to the middle is going to be exactly the same on one side as it is on the other. So we know that that's a straight line that goes all the way through the circle. And a straight line has an angle of 180 degrees. So any straight line, you could tag that somewhere, it's probably useful information. A straight line has 180 degrees, just like a triangle has 180 degrees. A straight line can be just kind of thought of as a flattened triangle. So a straight line is also equal to 180 degrees. So we know a bunch of measurements already, even if we haven't studied this before. We know a circle is 360, so a half circle must be 180. We know a straight line is 180 degrees. I think we probably would have seen that before. And that actually that opens the door for some new properties for us to use. So two arcs formed by the end points of a diameter. So here is the bottom half of that. Okay. The two arcs are both semicircles, and they're both the same, right? If it's 180 degrees on the top half, it has to be 180 degrees on the bottom half. So those are considered semicircles. And then I'll just remind ourselves in brackets, every semicircle is 180 degrees. The thing that might not be quite so obvious when you're looking at it for the first time is that even though it's a straight line, it's actually still a central angle. Okay, the first couple central angles we looked at, they were very clearly angles, right? It went from here to there to there. Okay, or another central angle could be something that went from here to there to there. Okay, as long as it went from the outside of the circle to the middle and then back out to the circumference of the circle, that's a central angle. Okay, could be small, they can be acute, they can be obtuse, but they can also be a straight line. So you have to remember that for some of these questions, that if you have a diameter, it is still going from the edge of the circle to the middle and back out to the edge, which means that this 180 degrees is a central angle, and that's going to be very important to recognize when you're trying to prove some of these is that even though it looks like a straight line, it's still an angle. Okay, a straight line just has an angle of 180 degrees. So the central angle of a semicircle is 180 degrees. Again, just a straight line. But we know from, let's look at the first property we looked at, central angle and inscribed angle property. We know that the central angle is always 2 times bigger than the inscribed angle. 2 times bigger. So let's look at this example down here. We have a central angle, a central angle on either side of the diameter. It doesn't matter which way you go. They're both central angles, right? You can look at it from the bottom or you can look at it from the top. So the central angle is 180 degrees. And we have an inscribed angle. And that inscribed angle is written in green. Okay? It starts at the same point as the diameter. Let's just label that A. Let's label that B. Let's label that C. And let's have our center as O. So the angle ACB, okay, is an inscribed angle. Angle AO, right through the middle, B, is a central angle. Now we know from our other property, an inscribed angle, so the green one, is half as big as the central angle. So if it's half of 180, it's got to be 90 degrees. So that's kind of a helpful piece of information, because whenever we see a 90-degree angle, what should we kind of start thinking about? You and the audience. Whenever you see triangles or circles and 90-degree angles, what instantly comes to mind? Pythagoras, that's right. I got a private message, and that person is correct. So now we can use Pythagoras, which means we can also solve for line lengths if we have enough information. Okay, so when you've got semicircles, most of the time you've got 90-degree angles as well. So that's going to help us out for finding line lengths of triangles that might look like this. Start and end on a semicircle. Okay, moving on to the last one here. Okay, the last one is just an extension of this one right here, the inscribed angles property, where I said no matter where you put a point on the outside of a circle, as long as they start and end at the same 2 points, or they're subtended by the same arc, they're always equal. Okay, well, nothing has changed. Okay, just because it's a semicircle, it doesn't change anything. Okay, these triangles all still start at A and all still end at B. It actually doesn't matter at all that they go through the center, only that if they go through the center, they're kind of special. They're still all equal, but not only are they all equal, they're all 90 degrees. So each one of these is still equal, but even more helpfully, they are also 90 degrees. So I can find all sorts of ways to find angles and line lengths, knowing that any angle or inscribed angle that comes from a semicircle, they're all equal and they're all 90 degrees. Let's see, all inscribed angles are equal and 90 degrees. Okay. And you only need to point at the angles in a semicircle property as your justification. Okay, now let's shorten these. I'm not sure every math teacher likes doing this, but I do. That's going to be the ASP, angles in a semicircle property. Okay, we'll go back to the other ones we did today. We've got central angle and inscribed angle property. Okay, so that's going to be a CAIAP. So that'll be a long abbreviation, but still shorter than writing the entire thing out. So that's our abbreviation for that. Inscribed angles property is just going to be IAP. So you can use that in your justifications. And then we already went through the ones the days before, the PCP 1, 2, and 3, and the tangent radius. Okay, so now that we know all of these things, and I know it's a lot, we've got, what, 7 of them? Now that we've got all these properties, okay, we could use those to start really dissecting some of the shapes that we see inside circles and some of the triangles we see inside circles, and then start figuring out hidden angles and hidden line lengths. And again, this is probably, you know, the one of the more difficult units as far as using your critical thinking skills and having to really think about what you know in order to prove angles instead of just kind of plugging something into a formula or an equation and figuring it out. But one step at a time. It doesn't always help to just look at X and say, well, I'm solving for X first. Sometimes you're going to have to solve for Y before X. Sometimes you're going to have to create a line so that you can use a property before you get to either of them. So just keep in mind, you can attack these up from any direction. Just start highlighting things that you know, and that will help you along. All right, so point O is the center of a circle. That's great. What I see instantly is I've got a central angle already made from A to O to B. So I know that's a CA, okay? So what is that, AOB? So I know angle AOB is CA. And you might not always end up using everything you identify, but at least you've got a starting point. So I know angle AOB is a central angle. I also know that angle ADB, that's a D up top there. I also know that angle ADB is an inscribed angle. So if I've got a central angle and an inscribed angle, I know that Y is going to be 2 times as big as X. So that's 2x. And how do I know that? That was the CI, central, or CA, central angle, inscribed angle property. That was the very first one we did today. So I don't know what Y is, but I do know that it's 2 times as big as X. So whatever Y is, X is 2 times. Whatever X is, whatever Y is, X is half, and whatever X is, Y is 2 times that. So I think that's going to help us out here because I am trying to find Y and I am trying to find X. But that first little chunk that I did there didn't solve the problem. It just kind of got me moving in the right direction. Now I need to look at the other piece of information they have because I can't solve the problem yet. So now I'm going to look at this inscribed angle right here that goes from A to C to B. And one of the things I should note for myself right away is that every angle in this is subtended by that arc. There are no angles that don't start at A and B. Okay, every angle in this drawing starts at A or B. And 2 of them are inscribed angles because they go to the outside of the circle, and 1 of them is an inscribed angle because it goes to the center of the circle. So I'm just going to write angle ACB is an inscribed angle as well. Okay, now let's start getting to proofs. And I want you to think about this. I could just keep working down these proofs, but then nobody's thinking about it. Okay. I would like somebody out there to tell me what they can use to figure out either what X is or what Y is. We now have enough information. Okay, don't worry about being wrong. Okay, just throw out some guesses and why you think X or Y might be a certain thing and why. Okay, I have a response in private here, so I'm just going to check that one out, and we'll see if that person hit it on the head here. Okay, so that person said angle ACB ACB is the same as angle ADB, because all inscribed angles are equal. Only if they start and stop at the same place. In this case, they certainly do. So that person who sent me the private message is absolutely right. So angle ACB, okay, equals angle ADB. That's great. So we know that from the inscribed angle property. I believe that was just IAP. And you will have to refer back, you'll have to refer back to these the notes of these little things. You're not gonna remember, because all the words are so similar, right? They all have like angles and property, and some of them have tangents, and a lot of them have inscribed angles and whatnot. It's no big deal to go back and just make sure you got the right one. So this person told me that is true, and I agree. That's true, ACB. And then we also know, in fact, before I put that IAP, I should also say, and it's 55 degrees. I don't have to prove that. They gave that to me. But I do have to prove or know why X is the same as this. And you need to use that property, which was, I believe, the IAP property. So we've already solved for X. So therefore, that's what those three dots mean. It basically means, so X is equal to 55 degrees. And we already proved it, and we justified it. We didn't say X looks about the same as angle ACB. So if they look about the same, they're probably both 55. You can never do that. Also, you can never use a protractor and measure the angles, because math textbooks intentionally make them a little bit wrong so that you actually have to use proof and words to justify it and find your angles and lengths. You can't just kind of say, well, they look the same, so they must be the same. Okay, so that person, who I will not identify just in case they don't want me to say their name, congratulations, that is exactly correct and proven very well. And Dade had the exact same thing going on the public front there. Absolutely, bud. I was in the private chat, but you had the exact same response, and that is correct. Okay, so great, we've got Y. Oh, X, I'm sorry, did I write? No, I wrote X, good. Okay, so that's great, X is 55 degrees. Now we've actually, we're done. The first step got us all the information there that we need to figure out Y. So what can we use to figure out what Y is? We've already got it up top. I just haven't quite put it into numbers yet. Y equals what? Y equals 2x. And I know what x is, right? So y equals 2 times 55. So y equals 110 degrees. Okay. Now the only thing that needs to be proved right here is, why does y equal 2x? Well, I already did that up here. I already justified it by saying that was the central angle, inscribed angle property. I wrote it up at the top because I didn't know if I'd need it or not. But it turns out, as soon as I got down here, I needed it. You don't have to write it again, CAIAP. You already proved it up top. So now I can just figure out finish the question, and I've already proven why it's okay for me just to write that y equals 110 degrees there. So we used 2 of those 3 properties for that one question, and that's okay.
All right, sorry for the audio disturbances. I'm having a little trouble with my microphone today. Let's look at example number 2 here. We say we've got rectangle ABCD. That's actually important right off the bat there that they gave us the word rectangle, because that tells us something about ABCD right away that's going to be super helpful. And that is that if it's a rectangle, all rectangles have 90-degree angles, right? So let's just note that right away. All rectangles have 4 90-degree angles. So that's going to help us right away, because now we know that this angle is 90, and that this angle is 90, that angle is 90, that angle is 90, which means we're probably going to be using Pythagoras. Let's just use, let's just make sure that we've got 2 out of the 3 line lengths that we need in order to do Pythagoras. And remember, it's always okay to add lines to your drawing as long as you're adding them in the proper place and you understand why what you've added is sort of, like legal and proven. So it's perfectly fine for me to add a line that goes from C through O to A. And any line that goes from a point on the circumference of the circle through the center to any other point on the circle, that's a central angle, right? Now, we don't necessarily know right now that COA is a diameter. I think it's probably one of the properties of a rectangle that it is a diameter, but we don't need to know that actually. What we need to know is that this angle right here is a central angle. Okay? That angle right there is a central angle. We already know that's a right angle. So let's just keep writing down things we know, and let's see how they relate to the circle properties. So we know that angle COA is a central angle of, okay, and then CBA, angle CBA is an inscribed angle. We know that angle CBA is 90 degrees. So angle CBA is 90 degrees. Okay, and how do we know that? We know that it's a rectangle. So I don't really need to prove that. I just need to say we know rectangles have 90-degree corners, right? Which means that if angle CBA is 90 degrees, that must mean that COA is a semicircle. So it's 180 degrees. Okay. And that is the C central angle inscribed angle property. So I know that for sure. Why? Because angle COA, or the central angle, is twice as big as its inscribed angle. Okay, so if you wanted to put further proof, 190 degrees times 2 equals 180 degrees by that property. So I do know that this is actually, it was easy to prove that this is actually a diameter, that this is actually 90 degrees, and now we've got enough information to use Pythagoras. If I just kind of pull that whole triangle out there just to make it a little easier to see, what we've got is something that looks like this, and we're trying to find the width of the rectangle, so I'm just going to call that X right there. So we're trying to find the width of the rectangle, and this is C, and that is B, and this is A. We know that from here to here is 8.5 centimeters, and we also know that C to O is a radius, which means that C to A is also a radius. My diagram is not to scale, but you get the idea, which means that C to A is equal to that plus that, which is 17 centimeters. So this hole is right there, 17 centimeters. We know that this one's 10, which means we can figure out X just by Pythagoras. So by Pythagoras, we know that the hypotenuse, remember always draw that line from the 90-degree angle, is 17. So it's going to be X squared plus, our other side is 10 squared equals 17 squared. So X squared plus 100 equals 17 squared is 289. Then from there, let's bring it up here. From there, let's bring 100 to the other side. So we got X squared equals, subtract 100 from both sides equals 189. Then we need to square root both of those. So X equals 13.6. Should probably check my math on that. I believe it is 13.6. Makes sense. Centimeters. So there we go. The length is 13.6 centimeters. And what we needed to prove or use in our proof is we need to know a little bit about rectangles. To get the 90-degree angle, we need to know that that is a central angle. It's 180 degrees, so we know that's a diameter, which means it's a straight line. And then we've got enough information to solve for that missing side. And I think that's all we were supposed to solve there. Hey folks, Dunbar here. If you were with me at the live session for 8.3, I noted that there are often several different ways to prove or use justification when you're figuring out angles and you're using triangles and circles. But I also said that I think that there was another more obvious way of solving or working through example number 3 because I didn't use any of the circle properties that we just learned. And sure enough, we can do it a lot easier, but we need to know one thing, and it's really hard to notice on this, and I just noticed it as the session closed, and that is that angle y, I was assuming angle y was just the little chunk that went from there to there. But even though it's really tough to see, it's there. By y, there's a little arc that goes like this, and what that indicates is that the entire angle is y, not just the little one chunk there. So this angle, the entire thing is y. Whereas when I looked at it the first time, and I think rightfully so, I just thought that whatever was on this side of this line was the angle y, which made the question a lot more difficult. Now that we know that angle y is actually the angle that is ABC, this question becomes a lot easier to solve. A lot easier to solve. And here's why. If I make a central angle at x, we know that angle y is inscribed, so that's an inscribed angle, and that angle x is the central angle. Therefore, okay, we know that 2y is going to be the same as x. And how do we know that? That was the C central angle inscribed angle property. So that was the first one we looked at today. Now, do we know what x is at this point? No, we don't. But this question becomes a lot easier once we understand if we either have y or if we have x, that we now have enough information to solve the entire triangle. So I think we said that angle x has to be 360 degrees minus the other two, and that that holds true. That's pretty obvious that that's just a circle there. So angle x had to be 360 degrees. Remember, we're not talking about a triangle because triangles have 180 degrees. We're talking about a circle, right? We're going from here to there, and then we just need to figure out what this little chunk is right here because we have the other two already. Yeah, we got the other two there. So if we know that angle, x is the missing chunk there, then that's going to be 360 minus 140 plus 100. And we did this in the video and got angle x had to be 120 degrees. So that is going to instantly give us what y is. So angle y then has to be half of that, right? Half of 120. So angle y has to be 60 degrees. Okay, and then once again, we already proved that, or already wrote our proof up here with the CAIAP, which just leaves us with the Z part. And the Z part, we can use an isosceles triangle. That works perfectly fine on that one. You can draw an isosceles triangle on this side. Now just maybe do it in blue just so it's a little bit more obvious. So once we know what those other two angles are, we know that this and this are the same because they're both radius, which means that this angle here is exactly the same as that angle there, and we already know that the middle angle is 120 degrees, right? So if we put all those things together, we can very quickly say that triangle AOC, I guess, triangle AOC is isosceles. And I don't know, again, if they expect you to just remember this, but angle AOC is isosceles because AO and CO, so that's AO and CO, are both radii, or the plural of radius. So if those are both equal, and we know one of the angles, we know that 2 times measurements. So as long as we say that we know it's an isosceles triangle, then we know that 2 times Z, okay, is going to be equal to 2 times z plus the other angle, which was 140 or 120. Sorry, that was the x angle that we needed to figure out first. 2z plus 120 equals 180, because all triangles have 180 degrees, internal angles. So then we just do the math really quickly, right? 2z, subtract 120 from both sides, and we get 2z equals 60, and then we get z divided by coefficient, and you end up with z equals 30 degrees. And I think those are the exact same numbers we came up with last time, aside from the y, because again, we had to know that the y was this entire chunk, not just the little chunk on this side. And I know, because I just double checked it, that in my quiz, and I don't want to show you the answers, but I do want to show you the quiz. In my quiz, I think there is a question that is almost the exact same as that. So I'm just going to bring that quiz up quickly to show you. I'll just pause the video here while I find it. Okay, here I'm back. I got quiz number 8, and I told you I'd try to give you some help to help you move in the right direction on this one. And what I wanted to point out was that little chunk right there on this thing, so you can see it, it includes both of those little angles there. So y is just the chunk on this side. The other side, that includes both of them, and that is 60 degrees. So I don't have a pen here right now. Maybe I'll just do a screen capture of this really quickly and bring it over so you can see exactly what I mean. Okay, but if I take this triangle, or sorry, this shape here, just move it over to my unit, new page. Okay, so what I'm saying on the quiz here is that you need to know, and it's kind of hard to see, is that angle right there is 60 degrees. That whole angle is 60 degrees. And that y is just this chunk of it. Okay, now here's the hint. DOB is a diameter, which tells you something about the entire angle and might help you figure out what that little chunk of that angle is. So there's a hint for the last part of quiz 8. I will also give you some more hints because I feel like I'm in a good mood. Why shouldn't you benefit from me being in a good mood? Well, I can just find where that quiz I was just showing you was. Oh, there it is. Okay, so let me give you some more hints on this one. Point O is the center, find X and Y. Okay, first one, you're obviously going to use central angle, inscribed angle. Second one, you can use either isosceles triangles, or you can use the semicircle property. And then for C, you're going to want to use the idea that a straight line is 180 degrees. That's going to help here. You're also going to want to use a central angle and inscribed angle. And then at the very end, when you're looking at Y, then you're going to be looking at the isosceles triangle again. So that should get you through that one. Use the properties of inscribed and central angles to explain angles inscribed, why they are right angles. I'm going to leave that one to you, but this one you need to explain it with a sentence or words, and you need to very, very carefully look at the properties of inscribed and central angles, and also what does a semicircle mean. So you kind of got to prove that one to me using your words. And then for this one, you don't necessarily have to do these in order. So if you feel like it's easier to solve Z first and then work backwards, or that's okay. Just maybe include little arrows if you proved something somewhere else. In this one, what have we got? We've clearly got DOB as a diameter. I already went through that. You've got that 60-degree angle that I talked about, so I'm not going to talk about that anymore. What else do you need to know? Well, angle W and angle Z, those both looks like they are inscribed angles that start at D and end at A, so that might give you some information there. DOA is also a central angle to D to O to A is a central angle, and D to B to A is its inscribed angle, so that's going to help you with X. and I'll leave it to you to figure out why. I think that should help you through that quiz. All right, take care.